Physics 100. I'm Professor Curtis, your instructor for this course, and this is the video lecture for Chapter 14, Gases. Let's get started. So we've already examined characteristics of solids and liquids. Now let's examine the characteristics of gases. The atoms of the material vibrating in place with very extensive movement relative to each other. So remember, in solids, the atoms are vibrating, but they're pretty much staying in place. With liquids, they have more mobility, but they're still more or less tethered to their neighbors. With gases, you've got none of that. It's a free-for-all. All the atoms are going in every which direction. This is the gas state. And because the atoms have that movement, gases lack rigid boundaries, just like liquids, and they're going to assume the shape of their container, just like liquids. Gases also have density. However, unlike solids and liquids, the density of your gas is going to vary significantly with temperature and pressure. Remember, with solids, the density does not vary with temperature or pressure. With liquids, the density can vary with temperature. With gases, the density will vary with both temperature and pressure. This brings us to a property of gases known as compressibility. Solids and liquids are what we consider to be incompressible. What that means is if you try to compress it to make it smaller, eventually you'll find a point where the material resists your effort to compress it. You've got it compressed as far as it's going to go. Gases, on the other hand, are what we consider to be compressible. This means that you can radically alter their volume and their density simply by changing the pressure. Speaking of pressure, gases conform with this pressure just the same as liquids do. Now, when we were looking with liquids, we were talking about pressure with depth. And gases have the same sort of effect when you're dealing with pressure. So, for example, the air that's above us is exerting a pressure on everything that's beneath it. The weight of all of those molecules is exerting a pressure. It's a force over an area. We typically don't feel this weight on us. And there's a couple reasons for that. The first reason is that the amount of weight that's upon us from the atmosphere isn't all that large. I mean, you're only talking about a little more than 100 kPa, and that's half of the pressure that you would see in a typical automobile tire, and about 1/6 the pressure you would get from a can of soda. And that's before you shake the soda can up. So you could see that the amount of weight that's upon us is not all that large. The second reason why we typically don't feel it is because we're accustomed to it. We've become acclimated to having this weight on our shoulders because we've lived with it our whole lives. Now, the pressure of the atmosphere is not constant. Okay, obviously, if you go higher elevation, there's less gas on top of you to exert pressure, and therefore the pressure is not going to be as much. It's also going to change with where you happen to be and what time it is. So that pressure on the planet is constantly changing, and this is what drives the different weather patterns. Changes in these pressures, this is what causes the wind to blow. This is what creates the weather. These changes in pressure that are constant, the pressures are constantly changing all over the globe. This brings us to an Irish scientist named Robert Boyle. Robert Boyle, as you can see, lived in the 17th century, and he investigated the properties of air. And his experiments led him to discover that pressure and volume are inversely proportional. And when you multiply pressure and volume together, you get a constant number. So for any system, the pressure and the volume, when you multiply them together, are going to be constant. Now, of course, that's a closed system. We have an open system where we can actually put gas in and out of our system, then, you know, that Boyle's law doesn't really hold up. But for a closed system where you're not adding or anything into the system and you're not taking anything out, then yeah, you're going to get constant product of pressure and volume. Mathematically, we can write that as PV equals a constant. But the more common form to express Boyle's law is what you see here, P1V1 equals P2V2, where 1 and 2 represent two different points in time. So the pressure and volume inside our system at one point in time has to equal the pressure and volume system at a second point in time. This means that if you want to change the volume of your gas, you can do so by changing the pressure. And the reverse is true. I mean, if you want to change the pressure on the gas, you can do so by adjusting the volume. Now, of course, here we're assuming that temperature is being kept constant. Think about this. Volume, which you see there in Boyle's law, is related to density. And we know that density for liquids and gases can change with temperature. So the volume that you get is going to be dependent on temperature. So we're assuming that we're keeping the temperature constant here so that that doesn't play into a factor. And of course, as I said before, we're assuming we have a closed system and not an open system in which mass can be entering or exiting the system. Now, to help illustrate Boyle's law, I found this awesome video where you get peeps. So, of course, he's got peeps. He's got them in a vacuum chamber. And when he turns on the vacuum, okay, the pressure is going to go down. So then Boyle's law says the volume has to go up. So you're going to see these peeps just explode. It's an awesome video. So here we go. Let's get this started.
What's up, guys? How you all doing? Easter is coming up, so happy Easter, and I thought might as well put peeps in the vacuum and we'll see what happens. We got a few peeps over there. Let's turn the vacuum chamber on, suckle the air out and see what happens. Wow, would you look at that? This is so cool. Look how much bigger they are. Wow, they actually imploded. Look at this. Oh my goodness. Look how much smaller they are. Look at this. This is what it used to look like. Now this is what it is. It's just imploded inside of it. Pretty crazy, huh? So if you break it apart, there's no bubbles inside of it. It's pure marshmallow. Pretty crazy. It's time to put a bigger one. We're gonna put one of those and couple chocolate eggs. Okay, let's turn it on and see what happens. Oh my goodness, look at it, he's going. Whoa, look at those chocolate eggs, they're so big now. And they imploded. Love it, love this experiment. Happy Easter, everyone. This one in ice, and this one into the hot water, and this one here. Woo! You see, it still looks like the brightest, but...
Yeah. So, I mean, hey, you know, it's like, it's Easter. Let's just put some peeps in a vacuum. I mean, doesn't everybody think like that? That is awesome. You know what? I had so much fun with this that I had to go get another video. So now we're going to watch bubble wrap in a vacuum. It's awesome.
What's up, guys? How you all doing? Last time I did a shaving cream in the vacuum and that was awesome. A lot of you liked it, and I also asked what should I do next. So there was a ton of comments. You should put bubble wrap in the vacuum. So let's do it and let's see what happens. So I got my bubble wrap, a big kind, so it looks better. I'm gonna stick it in a jar in a vacuum chamber. Boom, just like this. Let's zoom in a little bit. Now let's turn it on and let's see what happens. Oh my god, look at it! Woo! This is awesome! They all pop! Okay, let's get the air in and see what happened. Look at it, almost all of them popped. Whoa, that was so cool. Wow, look at this. Look at this shaving film. This is insane. It's just filling up this full.
Yeah, you can see that there in the end with the shaving cream that he was referencing earlier. And so, yeah, there's some awesome videos. But it illustrates the whole point of Boyle's law, where the pressure and the volume are inversely proportional. So for a closed system, which is what he had there with his vacuum chamber, when you change the pressure, the volume is going to change. So when the pressure goes down, the volume goes up. And then when the pressure goes up, the volume goes down. This leads us to Bernoulli's principle. Now, Daniel Bernoulli, a Swiss physicist living in the 18th century, and he took Boyle's work and he expanded on it by looking at the flow of fluid in terms of conservation of energy. In particular, he discovered that the velocity and pressure of a moving fluid are inversely proportional. So if you're looking at, say, the velocity of a fluid, there's a cross-sectional area for the pipe or whatever container the fluid is moving through. And then if there's a change in that area, then the velocity of that fluid is going to change accordingly. Now, one way to express this relationship is just like we saw with Boyle's law. So we could say that AV equals a constant, but it's more common to use this expression here, A1V1 equals A2V2, where A is the cross-sectional area of the pipe, and V is the velocity of the fluid flowing through that pipe. Now, Bernoulli's principle explains a lot of things. For example, this is why we shape cooling towers at nuclear power plants the way we do. Notice that curved shape. It's not just a straight pipe that's coming up to let the steam out. No. It's a curved shape to the pipe. Why does it have that shape? Well, Bernoulli's principle explains why it's shaped the way it is. So we've got steam that we need to release out from the plant, and so we put it through the tower, and as the steam is rising in the tower, notice how the curve comes in. So the area that the steam is going through in the pipe is going down. It's decreasing. Well, when you decrease the area, you're going to increase the velocity. So that gets the steam away out from the plant quicker. And that's what we want. We want, once the steam is ready to be released, then we want to get it away as quickly as possible. But we don't want to shoot the stream of steam out the top. We want it to come out more, I guess you could say, more slowly. And so we've got to slow it down before it reaches the top. So notice how, as you get closer to the top, the area of the tower is going to increase. And because the area increases, the velocity goes down, and that's what we want. So we're not shooting stuff up into the sky. It's more gentle. It's more of a floating type motion, which is what we want as it leaves the cooling tower. Now this brings us to Bernoulli's equation. Now, you don't have to know Bernoulli's equation, but think about what he was talking about with his relationship A1 V1 equals A2 V2. Pressure and velocity are related to each other, and really pressure and velocity are representative of different types of energies. So if these two types of energies are related, could it be that all other forms of energy are related with a moving fluid? And the answer is yes, and that's what Bernoulli's principle says. It's about conservation of energy. So Bernoulli expanded that idea to include other types of energy, and what he came up with was his famous Bernoulli's equation. Now, the full form of Bernoulli's equation, which you don't find in your textbook, but which is well known to many engineers, is what you see right here. You obviously don't have to know this equation, although we can actually look at the equation and identify the concepts that are represented in the equation, and it's the concepts that you need to be familiar with. Bernoulli's principle is really about the conservation of energy. So look at what forms of energy are on each side of your equal sign in your equation. The subscripts 1 and 2 are just different points in the system. So you've got a system, and we presume that it's a closed system. And we're looking at point 1 in the system where fluid is flowing, and then a second point in the system where fluid is flowing. That's the subscripts 1 and 2. What do each of these terms represent? Well, let's take a look at that. The first term we have here, P1, represents the pressure in the system at point 1. The next term is a kinetic energy term, 1/2 mv squared. Well, now, because we're talking about fluids, it's 1/2 rho v squared. Rho, the density, replaces the mass when you're talking about fluids. Potential energy of the fluid at point 1. So instead of mgh, now we've got rho gz. So you can see that it's a slightly different format, but it's actually organized the same way. This next term is the energy provided to the system with the pump. This is the work that the pump is doing on the system. And that's going to be equal to the pressure at point 2 plus the kinetic energy of the fluid at point 2 plus the potential energy of the fluid at point 2. And then we've got some energy that's lost in the system due to friction as the fluid runs through a straight pipe. And then we've got energy lost as it moves through different types of fittings like elbow joints and valves and whatnot. So you could see here that, again, you're not going to have to know this equation, but you do need to understand how conservation of energy is what Bernoulli's equation is all about. Energy is conserved in the system. And understanding that concept is what you need to know. Now, remember earlier when we talked about the density of water and how we looked at, say, okay, you've got these minor changes of density with temperature. How can this really be so significant? Well, Bernoulli's equation explains why that's so significant. Notice how many of these terms have density in them. Practically every one of them. The only terms that don't have density are the two pressure terms. Every other term has a density factor into it. So if you're off in your density by just a little bit, well, that's okay if you're looking at one term. But when you add that small error again and again and again and again, you can see how it really adds up. And so these seemingly minor differences in the density of water with temperature can compound quickly. And typically when you're looking at Bernoulli's equation, one of the things that engineers do with this is, okay, what size pump do we need to run the system that we're trying to design? Well, if you've got these errors in your density that are being magnified, then you end up making the wrong pump selection. And that can be very costly. So it's really important that you get those errors out, and that's why it's so important that we be as precise as we are with the density of water, because, I mean, water is a typical fluid that's used in a lot of these engineering systems. But again, the main thing you want to kind of understand with Bernoulli's equation is that it's about the conservation of energy. Energy is conserved for moving fluids within a closed system. And that brings us to the end of this lecture video. Thanks for watching, and we will see you in the next video.